Hi, everyone. My name is Veerisetti, and today I'll be talking to you about synthesizing a potential vaccine that combats the B.1.1.7 A570D variant of the COVID-19 virus. So to first start off, it's important to kind of understand what the scenario of the situation is. The COVID-19 epidemic has been catastrophic. We've lost a lot of lives across the United States and across the world to this very, very horrendous virus. I specifically chose the B.1.1.7 A570D variant just because I know that it's had a huge impact on the British countries. It's very, very important that we synthesize a very, very efficient vaccine to combat this strand of virus because it's taken so many lives across the world. And it's important that we use this research to help look into different avenues in fighting other variants of the COVID-19 strand as well. So I'm going to direct you to the background right here. In the background, it's important to see that we are introducing three mutations via site-directed mutagenesis. The first is the lysine to proline mutation. The second is the valine to proline mutation. And the third and final one that we're going to introduce is the alanine to aspartic acid mutation. It's important to understand that we introduce these two proline mutations because it is what produces the spike protein in its most antigenic form. And that is exactly what we want it to be. I've demonstrated two images down here, image B and C, to kind of show you the top down and side views of the wild type spike protein itself. It's very, very important, I think, to understand how the spike protein looks to kind of appreciate what's going on with this vaccine that we're going to create. So what's the aim of the study? The aim of the study is to comprehend and also to analyze the spike protein that's present in the SARS-CoV-2 virus. We also want to produce a vaccine that can combat this B.1.1.7 strand with the A570D point mutation. So what's the approach? The approach that we're going to take here is to undergo the wild type spike protein DNA will undergo a series of site-directed mutagenesis reactions in order to introduce those two proline mutations as well as the point mutation with the A570D introduction. It's also important to understand that we're going to introduce forward and reverse primers that are going to include those proline mutations as well as the point mutation. Then after we transcribe the DNA, we're going to synthesize a vaccine and inject it into a vaccine. Now, if we look at the results right here, by looking at figure D, we can see this linear domain map. This linear domain map of the spike protein kind of illustrates what domains the spike protein has, as well as where those mutations are going to occur. The A570D mutation is going to be added in the SD1 region, and the two proline mutations are going to be added in the CH region right here. If we look at figure E, these are the elements of the sequence of the mRNA vaccine. So we have the T7 promoter, which is responsible, the T7 promoter sequence, which is responsible for the T7 polymerase, which is going to transcribe our DNA. We have the 5' UTR, which is important because this is where the ribosomal binding site will occur for translation to occur. The spike protein, of course, is important to produce a spike protein with the A570D point mutation, as well as the two proline mutations. The 3' UTR is responsible for having the stop codon for the transcription process. And the poly A tail is responsible for preventing any sort of degradation of the mRNA itself. Now, if you could turn your attention to image F, we have the PGEM3Z vector. The PGEM3Z vector is where we're going to insert our mutated DNA using a restriction enzyme such as BAM-HI. Typically, we introduce two endonucleases. BAM-HI is just one of the endonucleases that we can use to kind of cut this plasmid vector. In image G here, we have the mutated SARS-CoV-2 spike protein, and I've highlighted the three mutations that we're going to introduce. The pink region is going to be the K986P mutation. The blue region right here is the V987P mutation, and the red region right here is the A570D point mutation. In future directions, it's important that we undergo in vitro transcription in order to see if any successful mRNA has been produced. We can purify the transcript, the mRNA transcript that we produced via HPLC. And finally, we need to have lipid nanoparticles in order to pack the vaccine as itself. We need to also conduct clinical trials to see if the vaccine is safe for humans, as well as if it actually does fight the virus in the proper manner. Last but not least, I'd like to say thanks to Parker and Dr. Roberto de Guzman for their help this semester in helping me conduct this research and in helping me conduct this poster. Thank you so much and have a wonderful day.